Thanks very much, Dave, and thank you everyone for being here this morning. I understand a lot of people were in town last night and there was a little bit of wine flowing, so I think it's great that you actually made it here on Saturday morning. So Dave mentioned my Rome Prize research. That was 6 or 7 years ago now, and this lecture and this kind of research really comes directly out of that. I won't bore you by kind of reading the AIA learning credits, but you'll be getting them. And here's kind of an outline. I'm going to give a little bit of an introduction. I'm going to describe the concept of architectural Darwinism, give a few exegeses or detailed breakdowns and explanations of a couple key construction details, and then extrapolate that into some broader general principles of durability that I think we should all carry forward in our design, and actually have a little handout on those that you can get on your way out. And then a closing, and then I'd love to take your questions and answers and discussion. So just to kind of knock off the effects of the wine from last night and maybe get the mind churning a little bit, let's start with this simple diagram. So which of these two kind of basic forms, a step pyramid or an inverted step pyramid, do you think would be a more logical, durable way to build? What's your intuition tell you? And I think that intuition actually counts for quite a bit. And which answer would a study of historic precedent suggest? Or maybe put more simply, if you look back through history, which of these two do you think you'd find more examples of through the past centuries and even millennia? So let that steep for a little bit, and we'll come back to that later. So the kind of subtitle of my lecture today and also my research project in Rome was In the Footsteps of Vitruvius. And of course, I'm preaching to the choir here. I don't have to tell you who Marcus Vitruvius Pollio was and that he lived and died in the 1st century BC. And of course, we know him most famously as a Roman architect, but I think it's really important to remember that the profession of architecture was a very, very broad hat in Roman times, and it really encompassed all that we would consider today as architecture and engineering, including every discipline, structural, mechanical, also included city planning, urban planning, and even military planning, forts, fortifications, and even designing things like catapults. So it was a really big and broad hat, and they were very, very talented people, polymaths, I think you would really consider them today. And even a master builder, a role that would go to a contractor today. So, of course, most famously, he wrote De Architectura, what we often call the 10 books on architecture, around 25 BC. And it was not the only architectural treatise from classical antiquity. It's the only surviving one. We know about the others mostly because Vitruvius tells us about them and describes about a half dozen others in our book. And I think we're very lucky that if any of the 6 or 7 were to survive, it was this one, because he actually describes them and says he's read them all and he's bringing forward and kind of summarizing the best points of each. So my research project in Rome wasn't really a study of Vitruvius, the man, the treatise, or his built work, and it wasn't per se a study of how Roman buildings were constructed, but I think that was kind of a means to the end of studying more about durability. And I was really inspired by his methodology, particularly in Book 2. And what he really did and what he described in Book 2 is he went back and he studied construction, Roman and also Greek, that had either proven durable or not. And he looked at both of them with a very careful and discerning eye and figured out and diagnosed why certain types of construction had proven durable and held up over time and why others had not and had kind of crumbled and fallen to ruins. And he looked at things as specific as what species of wood was used and how headers were laid in masonry and what type of mortar was used and whether rubble or cut stone was used. Just very, very detailed and insightful analysis. And so he kind of developed and published these in the manner of the day, which were scrolls presented to the emperor, so that all his kind of colleagues and all future generations could build more durably. And I just found that whole kind of process and approach and selflessness to try to better the profession to be really remarkable. And so my approach and goals in my project, though more modest and limited in time, were basically to kind of pick up on that methodology and carry that forward today. And so, of course, with Vitruvius living and dying in the 1st century BC and publishing his scrolls then, he basically, his study ended at that point in time. And Rome was kind of the perfect place and the perfect laboratory to pick up at that point in time and try to carry that idea forward by studying buildings from the 1st century BC, which exist in Rome, all the way forward. And I think it was a particularly great place for kind of all the reasons that you know, but also that they just have such a great legacy of really remarkable design and construction for basically every period since then. So classical antiquity, medieval, Renaissance, Baroque, and even early modernism. There are some just really great examples in Rome. So I think we're kind of all fortunate to practice, here in New England and in places like Boston, because we have a great legacy with respect to the United States of a great history of design and construction. But we're talking about 200 or a little more than 200 years, and of course Rome is a whole order of magnitude greater than that, where you're talking about 2,000 years. So in that way, it was also a great laboratory, and I think it was also a chance to kind of test some hypotheses that I had here. Here, freeze-thaw is a really huge issue in terms of how durable masonry buildings are going to be over time. Freeze-thaw is virtually non-existent in Rome, so what is it that's kind of making buildings fall apart there? So very different climate, different kind of tradition of construction. And a lot of the work I do at SGH, I kind of have all these great non-destructive tools and gizmos in our arsenal, so things like ground-penetrating radar and half-cell corrosion potential tests and borescopes and water testing and all that. And so I really wasn't able to bring all those tools with me to Rome and take them away from my colleagues. So all those I left behind. So that's kind of a lot of tools out of my arsenal that I didn't have in trying to look at durability in Rome. And another thing we often do, even with all those non-destructive tests, is you really want to verify, at least in one or two places, what's happening beneath the surface. So you can kind of correlate that non-destructive test with actual verification and see what's going on. This is a building in Providence with some problems with terracotta. So there's nothing quite like removing a small exploratory opening, particularly at something that's already damaged, and verifying exactly how was this really built and what's going on and how corroded is that steel, and doing these kind of hand sketches of exactly what was built as opposed to what was drawn, which are often quite different. So that was yet another tool that I didn't have in my arsenal in Rome, because I was not about to ask, and they certainly would not have granted permission for me to punch holes in 2,000-year-old buildings. So kind of two of my biggest tools were really off the table there. So how did I really go about this? Well, it was kind of back to old school and basics. It was really about looking, drawing, and thinking. And I know this group knows the importance of that, and of hand sketching, and of just looking carefully at what you see. And that's something I always stress with the kind of young staff that work with me is, you can snap a million photos really quickly, and then you forget what you've seen if you ever even recorded it in the first place, and it's just not registered in there. When you stop and draw a sketch, you're forced to stop and think, what's really going on here, and how does this connect to that? And you might start drawing it and realize that there's a little piece of information that you're missing, and you go back and you peek behind or under or beneath something, and you just can't do that with a photo. So I'm always, kind of the old school person stressing the importance of sketching and drawing as just an irreplaceable and invaluable tool. And one of my colleagues at SGH who teaches us internally a lot about how to use all these kind of fancy high-end non-destructive things like borescopes and ground-penetrating radar, one of the big points he always makes is the two best tools you have with you on any sort of building investigation or forensic investigation are the ones you always have with you. Those are your two eyes. There's just no substitute for careful looking and thinking. So in a way, the whole year was a great exercise of kind of getting back to basics on that and really thinking about it. And I think there's really an overwhelming need for more kind of research on durability, both in historic preservation and in new architectural design. And, I kind of came out of preservation school, graduate school, and I found that a lot, although it was great, it was very valuable, a lot of the focus is really kind of the micro scale. So exactly the constituents in a lime mortar and things that you're looking at the scale of a microscope or dental tools. And there was a lot at the macro scale. So what are the character-defining features of the building? What is it important to save? And the even broader scale of a district, and what are the character-defining characteristics of that district and that historic area. And there's very little at that intermediate scale. And by the intermediate scale, I really mean the scale of say, a window or a scroll or a bracket or a ledge or a balcony. And in my experience and kind of all the forensic work I've done at SGH looking at building failures and building problems, it's that intermediate scale that's really critical to durability. That's where buildings kind of live or die. So, here are 5 window sections. That's the intermediate scale. So the nitty-gritty of how does a window sill married to cladding, how does a flashing married to backup waterproofing, building paper, that type of thing is really critical to design. So, from where you're sitting, you probably have no idea why, half of these failed and half of them succeeded. And that's exactly the point, is you really have to look at these closely and get into the exact details of how does this flashing overlap that felt or Tyvek or whatever else in terms of how these are going to hold up over time. So it takes very detailed focus. And I think we're really in the midst, as a design and construction community and profession, of a crisis of durability. So, whether you're talking about just kind of lousy McMansions on any old cul-de-sac USA, these are from the east, or synthetic stucco, like drive-it failures in the southeast. So as a young engineer at SGH, I spent a lot of time in North Carolina and Georgia and the southeast investigating failures like this that were all on buildings that were less than 4 years old. And a lot of times they were even only a year or two old, and the sheathing was basically turning into mulch and these buildings were falling apart. To kind of, little bigger buildings, and of course, a lot of the McMansions don't even have an architect. They're just kind of put together by a builder. But this is a small regional hospital on the left in Ohio. So, not a huge commission, but, obviously an architect there and a team of consultants. And that building was leaking before they were even done punch listing it. And they had mold growth before they were even occupying the building. So that obviously is unacceptable anywhere, but particularly in a hospital. So that was, probably a year of my life figuring out what was going on there and helping them to fix it so they could occupy that hospital wing. To even the larger scale projects, so a really large, prominent commission by a really well-known architect with a huge, talented team of consultants and a very large budget. East Coast and West Coast I'm showing here as representative examples. So this was a lot of time and effort in my office. The top project, right across the river over at MIT was done by one of my colleagues, and the lower one was done by me. So that was another 3 years of my life here, figuring out all the leaks here and how to fix all of them, just shortly after construction and kind of making it right. So the point here is really not to criticize the architecture of the buildings I show. The point here is just to show that it totally runs the gamut. It's everything from small to large. It's East Coast to West Coast. It's north to south. We're in this crisis of durability. And so, why do we care? Well, one reason we care is we certainly don't want lawsuits or callbacks or unhappy clients. Another reason we care, I think, is about sustainability. So there's been a huge emphasis and push on sustainability and more recently resiliency in the past, 5 to 15 years. And, I think a really critical point to that is that durability is fundamental to sustainability. It's, the advantages are really obvious. So if you're talking about a building that's 100 or 200 or 500 years old, in the case of the lower left, and is still going strong and still very viable and useful building, think of all the 50 or 100-year buildings that would have replaced that if it were just a 50 or 100-year life. All the material that would have went to a landfill, all the embodied energy to create all the new materials and truck it or ship it to the site. It's a huge savings for the environment. The lower right image and the lower right image and the center one are a study that you can download from the National Trust, the greenest building. Actually, if you can back up one, Dave. And so what they did, this is a free download PDF. They had this whole team, including contractors, architects and all, that studied case studies of buildings, reusing a building, making it as energy efficient as they could, which was never as good as a brand new building, and kind of looking at all the life cycle cost, embodied energy cost, and which overall is better for the environment. And over 95% of the time, reusing the existing building, even though you didn't bring it to as high a standard of energy efficiency, was better overall from the planet than knocking it down and building a new ultra-high efficiency buildings. So it's an interesting study and a free download. So why then are we in this crisis of durability? In a way, it's really counterintuitive, because if you think about, we have much more sophisticated materials today, waterproofing materials, structural materials. Architects and engineers are trained and educated and licensed today in a way that they weren't 150 or 200 years ago. So how was it that farmers were getting this right and building durable buildings all around New England? This is a farm in my town of Winchester. And then you can have these very talented architects that come in and are kind of aesthetically inspired by this and do their own thing and have massive problems with durability from day one. So it's counterintuitive, but I think there are a few reasons. And among them are that when you're trying to innovate aesthetically, as Gropius was here in Lincoln in 1937, it forces you to invent all new details rather than relying on the details here. And it's possible to get it right the very first time you're trying something, but it's certainly not easy. And I think first and foremost, we're forgetting some basic fundamental principles of designing for durability. So in short, I think that ties back to this concept of what I call architectural Darwinism. So my work in recent years has been almost halfway split between, it's mostly renovation, and of that renovation, it's been about halfway split between these very traditional older buildings like the old State House on the right, or Lowell House at Harvard, which is a current project with Shepley, Rutan, and Abbott, and Holyoke Center at Harvard, another current project, 62 to 65, pretty significant modernist design. And kind of the other counterintuitive thing I'm finding is that there are more significant problems, and in my mind, more problems that relate directly to the original design, shortcomings in the original design, on the newer buildings as opposed to the older buildings. So why is that? Well, if you think about how traditional forms evolve, so let's pick a highly evolved architectural and structural form, like the northern French Gothic cathedrals, like Beauvais. Something like this doesn't just tend to arise instantaneously, kind of the lightning bolt idea to the designer at a drafting table, draws it, voila, there it is, it's all done. What really tended to happen over time was kind of a whole gradual evolution and a series of baby steps. So it's very, very difficult from a technical standpoint and a structural standpoint to make a very tall, slender, unreinforced masonry structure. It would be hard for us to do that today. So this kind of highly evolved form with flying buttresses and all, and it's pretty easy to make low, short, squat, very blocky, unreinforced masonry buildings. So you start out with something like this where they go from the semicircular Roman arch to a pointed arch. They start to open it up more and more. These are some baby steps along the way, some early Norman buildings in France. And if you look at cross-sections through the northern French Gothic cathedrals over time, so these are chronologically arranged from upper left to lower right, you can see them getting more tall and more slender, as we would say as structural engineers, which again gets harder and harder to make work under wind loads. So unreinforced masonry, the wind's blowing on that really hard. That's a very tall building. There's no steel, there's no reinforcement. How do we make that stand? So they evolved that form, and it was kind of a trial and error process, and there were some bumps in the road along the way. So Beauvais alone had 5 documented collapses during its construction. So they're both learning from their own mistakes, and they're learning from the mistakes of their colleagues in neighboring towns and in northern France, throughout northern France. So I think when we look at older surviving buildings from antiquity today, there's kind of a survival of the fittest that's gone on. So when you look at a building that is remarkably intact and has survived extremely well, like Pont de Gare or the Pantheon in Rome, those are the best of the best. And when we look at a ruin, like the Baths of Caracalla, it doesn't necessarily mean that was built poorly, because a lot of these were just plundered as quarries for free stone. But it does tell us that when we look at something that's totally intact, it was really well built, and kind of the typical preservation approach of less is more, do as little as possible on the intervention is really technically viable because these buildings were so well designed to begin with, and because they've proven the test of time. So I'd kind of diagram this process of architectural Darwinism like this. So when you have a new material or a form or method of building, like a tall, slender, unreinforced Northern French Gothic cathedral, people are figuring stuff out. They're figuring out how to make it work. There's a lot of trial and error. They learn from failures, their own, and from their colleagues who are trying similar things. And then a lot of time passes, and over time, through Darwinism, those that are evolved survive. And those with really serious technical flawed designs do not, or they're corrected along the way. So many centuries later, or even millennia later, we can preserve the survivors in this kind of less is more approach. And when we look at modern buildings, essentially we've short-circuited that entire process. So we've kind of cut out all that time. We've cut out Mother Nature, weeding out the lemons. And we've short-circuited it to there's a new material, a new form. Someone's trying something. They're trying to figure it out the first time. And then, maybe 50 years passes and we're trying to preserve it. And I think that's why I find working on these buildings so much harder, these mid-century modern buildings, these early modern buildings. There was such a force for innovation, and there wasn't time to go back and see what went wrong and to kind of incorporate that into a feedback loop so that we as a profession were building more durably moving forward. And to me, that's the big difference in something like the Wright Lock Farm, built by farmers over time. This is the 1820 barn. This is a 1923 squash house. So this is, roughly contemporary with the 1930s Gropius house. Of course, there were no plans or no architect on this, but I think this plate from traditional building materials, 1923, Philip Knobloch, is a great book. I've got some suggested reading on my handout, and that's in there. Shows basically that this was figured out. We knew how to do wood-framed clapboard buildings. We knew how to do doghouse dormers. And, I could spend a whole hour talking about how thoughtful all these details are at the micro level, just the way everything overlaps, the drip edges, the flashings, the underlayment, everything about it is incredibly well thought out, and you would do very well to build a building just like this today. They really had it down. Gropius came along and said, well, I'm really inspired by the austerity of this design, the simplicity, the taut volumes, the white envelope, but I'm going to put my own twist on it. Right? Instead of horizontal clapboard, I'm going to use vertical board. Instead of punch window openings, I'm going to use horizontal strip windows. Instead of wood windows, I'm going to use steel. He wasn't really used to the cold New England climate and all the condensation issues with that. Instead of this really well thought out sill detail, he kind of invented his own here that was mostly based on kind of the aesthetics and the lines he wanted to create, and didn't really think about getting water out or keeping water out. So kind of a lot of flaws with that really hurt the Gropius house in terms of trying to be durable. So the passing on of the knowledge and this accumulated knowledge can happen in a couple ways. It can happen through architects, as in, kind of builder handbooks or professional associations. It can also happen directly through the builders and through the foremen themselves and passing it on to apprentices. But I think what's often not understood today is kind of taking that accumulated knowledge and the value of all that knowledge in traditional building and traditional construction. It's often taken for granted, and people don't appreciate just how valuable it is. And sometimes people look at a detail today and think it was really just for aesthetic or ornamental or stylistic reasons and don't realize the technical logic that underlies it. So I'd like to try to quickly take 3 examples of that and break it down for you and try to work at kind of 3 different scales. So one is the scale of a whole facade. These kind of forms, all this articulation, band courses, window pediments, etc. The scale of an element itself, a window, and then how 2 different elements, a wall and a roof, come together. So this kind of common eave detail. So these are all super common things that you would find in Rome. Windows like this, facades like this, eave details like this. How does each one of these work? Are they just purely stylistic, or is there something more to them technically that's going on here? So let's start with the facade forms. So you could walk up and down almost any street in Rome and see buildings like this. So here's on the right looking up from the sidewalk, from the top looking down for the roof. And I think, people tend to look at all the band courses, all these kind of projections, projecting sills, projecting heads, and think, well, that's all just kind of the style of the day. And modernism comes along and says, well, we don't really need all that. That's just kind of, pointless ornamental frippery, and we can strip it down and do something that's more true to our own times. So here's a section through one of the buildings I studied. It was a 1790 building. And then here's kind of a conjectural section of modernism saying, we don't need all that. That's not of our time and place, and let's just kind of clean this up. Let's get rid of this roof overhang and just make it a parapet. We don't need all this stuff. Let's just kind of have a nice, simple, planar facade. So if none of this is doing anything for a living, if it's all just ornamental, then that would be perfectly fine. We could do that, right? But the question is that doing anything? Well, it is. And, so the way these walls work, so these are, the technical term would be load-bearing mass masonry walls. So you have very thick load-bearing walls, which work structurally. A lot of these walls are, 2 or 3 feet thick, solid masonry. And that works really well for carrying all the gravity loads of the floors down to the ground. But the way they work from kind of a water management standpoint, you can think as if, if we were to cut a section here and we were to tint the water blue and start spraying water on this wall, what you'd see is there are 2 forces acting on the water. So gravity is bringing the water down, and absorption and capillary action is simultaneously bringing it in. So the kind of gradient, if you could see where the wall is wet and slice a section right through it, is actually migrating inward and forming this triangle. So at the point where that moisture, might be free water, might just be moisture, gets to the inside, that's where you have a problem, like either a free water leak or it might be all that blistering, plaster and paint and everything else. So these are, 5, 6, 7-story buildings in a lot of Rome. So you pretty quickly get to that point. How do these buildings work and not have that problem? Well, the way they work is these ledges and band courses are very functional because they're basically acting like a through-wall flashing would today for us in a cavity wall. So structurally, these band courses that might be something like travertine, structurally, those want to project deep into the wall to be structurally stable as they stick out. These are not just, glued-on ornamental details. And with just a very slight wash slope to the outside, these essentially act like flashings, and they're basically resetting the clock at every floor line. So instead of having this gradient of water get to the inside and causing all these problems, it gets it out at every floor and kind of manages it on the way down. So that's really how they work. Kind of an example, this is a very utilitarian medieval fortification, 10th to 12th century, where they were just designed with they were concerned with protecting themselves from the invading hordes, right? And they were less concerned with a lot of the water management issues. So you can see that instead of a 70-foot tall building, this is probably only 25 or 30 feet. It doesn't have any of that going on, and this is that same corner viewed from the inside. So you can see all the water-related damage in the absence of those features. And this is from Ercolano Scavi, so one of the towns that was buried by the eruption of Mount Vesuvius, in the shadow of Mount Vesuvius in the Bay of Naples. So like its more famous neighbor Pompeii, this is a great town to visit. And I think you can actually see more here, although it's smaller than you can at Pompeii. But one of the things here, this is what you might call a pent roof today. So just a little, was never a porch or a loggia or anything like that. That was all there was. It was this little, 1 foot, 1.5 foot wide roof. And because ancient Roman roofing tile have a chamfer at that back edge, they always have a chamfer, and I could see the chamfer on all the tiles that are all over the ground as well. The chamfer's not visible here, so I know that those project a ways back into that wall. So here's my sketch of what that probably looks like. And just like today, this was kind of a pain in the neck to build. You would think that the contractor would say, wouldn't it be much easier if we just build the wall all the way up nice and straight, and then we come in and we put that little thing on the outside and we can just frame it in there or something. But they went to the trouble to do this and bury that tile and that roof in the wall. To me, it means that they understood that principle, just like the band course and just like a contemporary through-wall flashing, that you have to capture the water that's absorbed back into the wall and then get that out before it gets to the interior. So that was a very telling detail. At the scale of a single element, I'm going to pick this Renaissance or Neo-Renaissance window. So you've all seen a lot of windows like this. You can even see some in the Back Bay and right over at the Boston Public Library. Very common form and common throughout Rome. Whoops. So, there are a lot of really great things about this, and in my mind, this is a really integrated design in terms of managing water, structural, architectural expression, etc. So this is actually from a neo-Renaissance building from 1790, not from an original Renaissance building. This is the Palazzo Bronski, which is one of the branches of the Museum of Rome. It's right near Campo dei Fiori. So structurally, these scroll brackets are actually functional. They're helping to hold up that projecting lintel. The beautiful pediment is, structural. This is shedding all the gravity load from this very thick wall. So this is the section through this building. So this very thick wall here, putting it into each side at the jamb, and this allows them to make this wall right here very thin. So you can see that wall's very thin here. And that's really important because if that wall were 3 feet thick, you could never get to that window or open it up. Our arms aren't that long, right? So structurally, they're enabling that by using the lintel or the arch in some cases to get that load over to the side and allow that wall to be thin rather than thick. But there's kind of a challenge that comes with that. So think back to our diagram of the gradient of water. If all of a sudden you have a super thin wall here, then it's going to be a challenge to make that work and be able to absorb water and not have a lot of plaster staining and damage on the inside. So really, the pediment, in addition to kind of all the beauty and the classical references here, every little detail about this and all these overhangs are also very, very functional drip edges to get water off here and clear it off and try to get it away from this area that we know is particularly vulnerable. It's still vulnerable as well because if you think about, I'm sorry, David, could you back up one? So if you think about water that's hitting this facade, what's hitting here is in part absorbed by the brick and is in part cascading down over the surface. The glass is totally impervious and non-absorptive, so everything that hits this window is being funneled to this point right here. And that's where you have a very, very thin wall underneath. So what sort of magic happens to make this work and not just have a massive amount of leakage and damage under this? You need a really good sill detail. So they really needed to think about this. So just back to the top of the windows for a moment, I think when you look at Renaissance palazzi, there are a lot of variations on the theme of what these windows look like, but they usually have some sort of slope to them to shed water, and then the ones that are very flat usually end up having problems like this, and then being capped later because of deterioration at the top. So that's an example from Palazzo Carpegna. But kind of coming back to the water issue, so back again to our utilitarian medieval fort, the very thin wall here, all sorts of damage, peeling paint, mold, plaster damage. Again, all the water that hits the glass really gets cascading down right to point A. You've got a very thin wall. What do you do here at this very thin wall to manage that? So what they did on Palazzo Bronski, and this amazed me, and I couldn't believe it, and then I saw it later on a building in Venice, and then I saw it later on another building outside Rome, so it wasn't an isolated incident. It's just this very, very clever scheme. You can see it here carved into the travertine. So there's a trough here to collect all that water. This trough, this all slopes this way. Then there's a weep here that's drilled through to get that water out. And then back inside here, there's another trough, marble, and then there's a pipe drilled through here, a lead pipe, and they've actually soldered the lead pipe to the trough, and there's a little weep here. So you can see there's a dot, those are weep holes. Every window in this palazzo had this. And they were restoring it at the time. The Italian architect, who was basically from kind of the Landmarks Commission of the city of Rome, swore that was original to the building. It hadn't ever been retrofit later. And they said it worked beautifully, and they weren't even touching it. So that was just, in my mind, an incredible technical design for water management in this 1790 building that I also saw in a couple others.
I'm sorry, can I interrupt on that?
Sure.
Would that work with any wooden material, or is it only because it's stone that it works so very well?
Yeah, it's a great question. I mean, obviously any sort of wood sill needs to shed water as well because it's even more vulnerable to deterioration, but the stone is better suited to act as a trough for water over the long term, which is typically why with wood sills we're often relying on something underneath like a metal flashing that's concealed under the wood to help keep the building watertight even if the wood is taking on water. And then kind of my final common detail is how two different systems come together, so roof and wall. And this detail really caught my eye, and one of the reasons was, well, obviously it's really beautiful, but one of the reasons it really caught my eye initially was you had buildings out in Rome that were 200, 300, 500 years old, and they had all this exposed wood. And obviously it wasn't pressure treated, in that day and age, but it wasn't ever painted. This is all just kind of darkened from oxidation. Never painted, never pressure treated, and it wasn't anything like cypress or cedar or naturally decay resistant wood. This was typically just pine. So how do you and Rome's a very rainy climate. It doesn't snow there in the winter, but it rains all winter. So and it's very humid in the summer. So rain and humidity are conditions that are very conducive to wood rot. So how do you take a wood like pine, not paint it, not pressure treat it, put it out in a rainy, humid climate for 500 years and have it last? It seems almost impossible. So there are a lot of clever things. This is Casa di Dante in the Trastevere neighborhood of Rome, and this is a section of the same detail. So what you're seeing here, essentially, these are the attic floor beams or the bottom chord of attic roof truss that project out here and here. This is a little dark, about every 10 feet. This is a continuous horizontal rail that runs between them, and then that rail supports all the rafters, which are at 1 foot on center. So that's kind of the basic construction. And so again, medieval buildings, older buildings, Renaissance buildings, and the McKim, Mead, and White building that I was in the American Academy in Rome had almost the same detail all the way around the cortile, the interior courtyard. So it transcends periods, styles, centuries, generations. You change these styles drastically, and this detail just keeps going and going and going and being repeated again and again. So that's a big hint right there that it's not just stylistic, right? If it was stylistic, it would be changing every time the periods and styles change, but it's very constant. So that's our clue here. So how does this thing really work, and how does it not rot? Well, this, too, is, in my mind, a beautiful kind of integration of structural, architectural, envelope, water tightness considerations. So in terms of structural form finding, let's talk like Louis Kahn for a minute. This is the form it wants to be structurally. So if we looked at, we've got a cantilevered member with a point load at the end. It basically wants to be a triangle because that's the moment diagram for that member. So everything below this half is unnecessary. You don't really need it structurally. And then you might think, well, why bother cutting it off? It's easier just to do a straight cut rather than an angled cut. And the reason you cut it off is actually preventative, because when you have a straight member that's out in the rain, you've got all this end grain to absorb water. And then think again about our gradient of water. Gravity's taking that water down, the end grain, wicking, capillary action, absorption are taking it in. So when you end cut these, expose the end grain to the weather, this tends to be the pattern of rot. And as the owner of a 1914 bungalow that had straight cut joists like that, I can personally testify that that's exactly how they rot. So you want to cut that off, cut off the cancer before it infects the whole structural member. And then you might think, well, you could just cut it off at that straight angle. Why do you need all these little kind of ornamental doodads? Isn't that just ornament? Well, those are beautiful, but they're not just strictly ornamental, because when this does get wet, what you really want to do is you want to shed that water as quickly as you can. So those create a whole series of drips to get that water off. And I'd also want to point out that when you look at this beautiful element, the rafter overhangs it. The stop, which keeps the decking from sliding off, overhangs that, and then the clay tile overhangs that. So everything overhangs everything else. So as water comes down off this roof, it's not curling back around here and getting this wet. It's clearing it straight off. And then if you think about this angle, even in a 45-degree wind-driven rain, which is pretty severe, this never gets wet. So that's how they made pine work in this rainy, humid climate, untreated, unpainted, and never rot is, A, keep it so it almost never gets wet. It takes almost a pure horizontal rain to even get this wet. And then when it does get wet, you get that water off it very quickly. And then by having it unpainted, I think it's an advantage in terms of the drying potential. It dries out really quickly, just like an untreated cedar shingle, particularly up at this height where the wind's really whipping by and past all these buildings. So that's how this has survived for all these years and done so well. And you see this going way back. So again, just a few examples. This is a Spanish school that was in my neighborhood. This is turn of the 20th century building. And then this is going back to 79 AD, another building at Ercolano Scavi, buried by Vesuvius. So here it's the same kind of variation on this theme. And this particular instance, they actually extended this way out over this sidewalk. And there's a sidewalk here that almost exactly aligns with the roof. So, it's protecting runoff from this framing, and it's also helping to make these walls more durable as well. And just a few close-ups, because I think it's really interesting when you can see original wood framing from 79 AD. That's one of the things you can see at Ercolano that you can't at Pompeii. The nature of the kind of burial by volcanic material, mud and ash, mud versus ash, kind of preserved wood at Ercolano, whereas Pompeii really didn't have much, if any, surviving wood. So this is a recarved replacement. This is an original piece of wood, overhanging cantilevered structural member from 79 AD. And even a detail that's seemingly as minute as, well, how far exactly should that clay tile overhang that wood? I was surprised to find that is a highly, highly evolved detail. So one of the first buildings I was on the year I was in Rome, Palazzo Cenci, that's where the RISD program in Rome was located, and they were very kind to let me into their building. Their courtyard was being renovated. So a very rustic little courtyard here, and the foreman told me right away, he was redoing this roof, that this overhang should be exactly 7 centimeters, 7 or 8 centimeters, which is about 2 3/4 inches. And what he explained was that if the overhang is too short, the water curls back around and all this wood rots. And if the overhang is too far, then someone puts a ladder up there, goes to maintain the roof, and it snaps off under the weight of the ladder or the worker. So that 7 or 8 centimeters, that 2 3/4 inches was perfect. It was kind of the Goldilocks dimension, not too much and not too little. And so that was one of the first buildings I saw the whole year. And then every building I got on after that, when I get up on the roof, I put my tape measure on there, and sure enough, he was right. It didn't matter if it was an ancient building, Renaissance, Baroque, Bernini building, Borromini building, they were all spot on 2 3/4 inches. So kind of an extrapolation of this idea is that, I think it's great to design windows like this, and I obviously have a huge amount of admiration for, the Renaissance window. So, whether you choose to design a traditional building or whether you choose to do something contemporary, this is a chapel by my friend Kyle Moe, I think it's important to learn these lessons and start to think about projections and shedding water and all those good things, whether it's contemporary or traditional design. Don't just think about flush and clean and plainer. It's important that every building be durable and every building think about water management, because every building's going to get rained on. So extrapolating this into some general principles of durability. So here are the principles. They're in the handout I have ready for you. I won't read them one by one, but we'll kind of go through some examples. So let's come back to this. So I think I heard a few step pyramid when I put this up originally, and I kind of set you up and led you down that path, because I think a lot of people's intuition would tell them that that's more logical. Trying to think back of examples of either throughout history, you might think of like a Mayan step temple, kind of the kids' blocks that are all over my living room floor tend to have that kind of step pyramid profile. So we might be thinking about that. But it's really the inverted step pyramid in my mind. So the reason that I'm going to argue for that is this. So if you think about the way the two manage water, the step pyramid, and Pradoc's Thousand Oaks Civic Arts Plaza was a good example of that. You've got kind of all these surfaces and all these interfaces of wall to roof to wall to roof to parapet intersection that are just going to be torture tested by the rain and water. So when you think about the way a 45-degree wind-driven rain hits that, there's absolutely nowhere to run and nowhere to hide from the rain. Every little intersection has to be perfectly watertight, and you need perfect membranes and all that. That's a pretty high bar. If you think about the inverted step pyramid, even a 45-degree wind-driven rain, it's really designed to shed and shelter. And so what I mean by that are the blue arrows are shedding that water right off the facade. And most importantly, with that configuration, you don't just dump it on the next floor down and kind of relocate or transfer the problem. It clears it all the way to the ground. And then those red areas, which are what I would consider sheltered, they never even get wet in a 45-degree wind-driven rain, like the eave overhang detail from Rome. So you can see the value of how well that has worked for centuries in Rome. So that's the reason why I think this, though counterintuitive, is actually a more durable way to build. So we might think, okay, yeah, Boston City Hall Plaza, that's kind of got that shape, but that's very modern. Do you really see examples of that throughout history? And if so, what are they? Well, about 3 blocks away from Boston City Hall is the second oldest building in Boston, the Paul Revere House, 1680 to 83. And when you look closely, it is definitely there. So every one of these floor-to-wall intersections, you get that overhang, you get that inverted step pyramid form. It's not as exaggerated as my kind of schematic sketch, but it is nevertheless definitely there. And of course, that design and that kind of early construction in New England first period houses, those come to us from kind of English Tudor and Elizabethan precedent. And whenever you look at a good example of that, either an original one in England or some of the good period reproductions, early 20th century period revivals, it is always there. But what really surprised me, once I started seeing this, then all of a sudden I've got this kind of disease where I can't stop seeing it, and I'm seeing it again and again in other periods and styles. So whether you're talking about like a Queen Anne Victorian from the late 19th century or a Greek revival from the middle of the 18th century, often it's there in one form or another. So it's really just a durable way to make wood buildings, wood not being an inherently durable material, more durable by the nature of the way we design the building enclosure and form. So of course it's shedding and sheltering, and when you go and look at the actual early English examples, 15th century buildings, it's no surprise that they evolved this very, very clever way of making the envelope form make inherently non-durable materials more durable. So they were building with untreated wood that was not, cypress or cedar or mahogany, and they were infilling it with wattle and daub. Wattle and daub is basically wicker. Here's a cutaway section on Shakespeare's house. It's basically wicker that's, kind of filled in with clay or lime plaster. So if you took a panel of this and put it out in the yard, this would turn to oatmeal really quickly. This is not a durable material. And actually, Vitruvius just totally decrees it in the 10 books. He says it's a horrible material and he wished it had never been invented because it's so non-durable. But they were clever enough, the English, to come up with a way to make it durable, which is all about the form of the enclosure, as we've discussed. And, it's not just in wood framing that you actually see this inverted pyramid form. So if you walk around Venice, all right, think about a city that gets really tortured by the weather. All right, take a city, build it in a saltwater lagoon where it just gets pummeled by every storm that rolls in off the sea. And the area that particularly gets the most pummeled is south and west of the Grand Canal, which is, kind of the ocean-facing half of Venice. And you walk around that ocean-facing half of Venice, and that's where all these slides are from. And you see it again and again in masonry buildings. So here they were cantilevering out and making masonry buildings do this. Obviously, that's not easy. And in some cases, they're doing it with stone corbels. And in some cases, they're actually doing it with wood. So you see that here and here. And these are just, very average run-of-the-mill buildings in Venice. I think this is a particularly beautiful example where the floor joists come through And then where they have a demising wall and hence greater load because of the load of the masonry, then they put in these kind of beefy travertine corbels. And then also big roof overhang here. And we talked about the importance of window pediments and hoods sheltering the top of windows from rain, particularly in the days before they had gaskets and sealant and butyl and all that stuff. So this to me is just a beautiful expression of an envelope and overlooking a little piazza in Venice, and then having kind of these projecting window hoods double as balconies, just a really nice urban gesture overlooking this little piazza. So there are other ways in addition to the inverted pyramid form that are kind of the same mindset but are slight variations. So the Pantheon, here you have, back on the main portion of the building, which is the drum, the walls themselves are planar, but the band courses actually project out beyond, each one projects out beyond the one below. And it's a little hard to tell in this photo. It's a little beat up after 2,000 years, but every architectural and archaeological reconstruction drawing of this is very clear that that's the configuration, and the uppermost one projects out the most, etc. And of course, the importance of that, as we discussed, is when you clear the water, you clear it all the way to the ground, and you're not just dumping the problem and the water on the next story down. So that, in my mind, is a great variation on that theme. Another one, kind of moving forward into the Renaissance, is at Palladio's Basilica in Vicenza. So this, of course, was his famous remodeling of an earlier medieval building and kind of wrapping it in this beautiful marble loggia. There's a medieval building working under there. So here at Palladio's loggia, the walls are planar. The band courses and ledges themselves are planar, but he's got these projection. These are essentially like a copper scupper, what the Italians call a dolcione, which means big shower. And when it discharges all the water off this balcony, it does turn into a big shower. And the important point is it's clearing it all the way to the ground, and it's not just dumping it on the level below. So again, very thoughtful design and a variation on that same general theme and general idea. So these are all about water management. The thing I found in Rome is that even though they don't have freeze-thaw, the restoration architects and conservators I met and talked to there said, time and time again, deterioration, it's all about water. Water's the foremost agent of deterioration, even in the absence of freeze-thaw. So water management is the first and foremost principle, and you need to shed and shelter. So lots of ways to do this, and it's important to do it both at the overall building form, ledges, band courses, roof overhangs, and individual elements like window heads. Second principle is put each material in a position to succeed. So, we saw with the English precedent and the Tudor and Elizabethan architecture that it's not always about using all the best materials all the time. It's not about building everything out of granite, but the materials you have, use them and detail them and position them and design the enclosure in such a way that they're positioned to succeed. I thought one really great example of that was, again, this little seaside town of Ercolano that was buried by the eruption of Mount Vesuvius. So they had three basic types of stone getting out of the ground there. They have basalt, which is the very, very dark black stone that you see paving many of the streets of Rome, the little pietrini, the little kind of square cobbles oriented in a diamond shape or other shape. So that's highly durable. It's even more durable than our own granite. So rather than using that beautiful black stone in the most kind of precious or conspicuous places, they used it where they needed it the most. So they paved the streets with it. And you think about this is, you've got water kind of ponding between the curbs. You've got hoofed animals going over that. You've got wheels. These were metal-lined wheels in that day going over that. So that's really taking a beating. It's sitting in the water, etc. So that's where they put the most durable stone. They had a stone of kind of pretty good intermediate durability, tuferositas, which they used on the curbs here. So still a pretty harsh environment, but not as harsh, not submerged, not kind of taking all the, the hoof and wheel impact. And then they had a stone that's just terrible, and it just totally falls apart, kind of like our Portland brownstone that, the Back Bay has been dealing for years with kind of repairing and restoring and refacing. And this is it right here. It's a very beautifully colored yellow stone. Here's a close-up of that wall. So this was only excavated about 1920. This building, unfortunately, no longer has the overhanging roof to protect it. And, this kind of looks like bad repointing that's spalled off the stone. That's actually original Roman mortar, and this stone is so non-durable that it's essentially lost a durability contest with the mortar that was used to put it in place. So nothing wrong with that mortar, it's just a terrible stone. So the way they made the stone more durable was big roof overhangs like you see here, and then a sacrificial coat of plaster on top of that. So keeping the water off it, and then if something's going to get wet and deteriorate, it's not your structural wall, it's just this kind of sacrificial plaster parge coat. And, even Bernini, working for the Pope in the Vatican, did not have an unlimited budget. So when you walk around his beautiful colonnade at St. Peter's, 1556 to 67, this was under restoration when I was there, and I was very fortunate to be able to get up on the scaffold. And so this forest of columns is true solid travertine. The friezes and the statuary and everything else that you kind of see on the outside here is all travertine. But once you get inside the colonnade, and this is multiple bays and layers deep, this was a mock-up during the restoration. These are actually faux painted flat brick arches that are plastered over and then faux painted to look like travertine. You would never know from the ground, and I think from a durability standpoint and a budget and an aesthetic standpoint, he used the real stone in the right place, and then he used kind of the fake stone in the right place too, and it's holding up really well. So he was smart about where to put the money in the budget. Next principle is that the durability of an individual building component should be proportional to the consequences of failure. And so here are a couple examples. This is an iron hinge from just a really rustic little building kind of in the back of the Villa Farnacci that was just, kind of a wood shop. And it's corroded and it's in pretty tough shape now, and they were replacing it when I was there. But I think that was fine because it was in a place where they could get to it easily. There were really no consequences of failure. That corrodes out, the drawer drops a 1/4 inch, no one gets hurt, and you replace the hinge. Same thing here. This is an early 20th century modernist building, 1937, in a natatorium, high chloride environment. They mixed a couple different metals here, steel and bronze, and that's kind of corroding. There's probably some differential galvanic action going on between those two metals. But again, that's okay. They can get to it. They can replace it easily. And that door probably drops 1/8 of an inch if that hinge corrodes and drops. So although these are having problems now, I think that's totally okay. Now, here in the Imperial Roman Forum, the Roman connections of stone to stone, these were not just mortar that was laid stone on top of stone like we would do today. These were actually typically dry joints, no mortar between them, connected with bronze dowels. And then the bronze dowels were sealed in lead, and then this is a little lead channel that runs out so the excess lead can flow out the surface. And that was pretty typical. That's how the Colosseum stonework was built, and that's how a lot of these were built. And so the beauty of that is, if you had mortar in here and it deteriorates, you've got no sort of connection. This isn't relying on that. The bronze is a very durable material. It's not going to corrode, and it's very ductile, which is also important because they're in a high seismic region. So these are very good connections. Here's another bronze strap connector, and even the Pondigar. Other than the very top course, which carries water, the rest of it is all dry laid. There's no mortar whatsoever in that entire construction other than the top level. So, but obviously, let's say they put this together with iron, and the iron corroded. I mean, there's no way to get to that to inspect it. It's very difficult to get up there and replace it. And then when it fails and it starts to spall the stone, you've got tons of stone that are falling right down on people's heads. So really, they put the bronze, the kind of precious and expensive material, not where everyone would see it, but where they needed it the most from the standpoint of durability, just like the basalt paving in Ercolano. So kind of the counterpoint to that, and the really disturbing trend that I've seen in looking at a lot of spec residential buildings that are being thrown together and are falling apart very quickly, is do just the opposite. So everything that's concealed gets built with the cheapest possible materials imaginable because the client doesn't see it. And then what's exposed, like the kitchen countertops and the refrigerator, heaven forbid it's not a Sub-Zero, that's where all the money goes, is where the client sees it. So this is my little 1,300 square foot bungalow 8 miles north of here. And my wife and I reshingled this some years ago. And, although it's about 100 years old, the sheathing was in perfect condition. There was absolutely we didn't replace a board. And they had put a metal flashing on the head of every window, and they really thought about the subsurface detail. So although this was a very modest house, the kind of, more opulent houses in the neighborhood have oak and maple and hardwoods. In our entire house, every floor is pine, every piece of trim is pine. It was a real modest, small house. They designed it durably, and they put money into the concealed things rather than the exposed things. And that's the way to go in a limited budget for durability. And kind of the final point here, I think, and maybe the most important one as you're designing, is to recognize that any design, even a really good design, has some inherent vulnerabilities or an inherent Achilles heel. And it's really important to recognize that while the design's still on paper, and then design in such a way that you minimize your susceptibility to that. So kind of an example of that, this is an early modern building in Rome by Luigi Moretti, really great early modern architect who's kind of been being more and more recognized in the past 5 or 10 years. It was essentially like a YMCA. This is kind of like a gym for the youth of Rome. Beautiful spiral stair he did here. The outside's pretty neglected and in rough shape, but you can see some of the beauty in the original design in the interior. So in the kind of main gym of this space, he had this concept that he'd love to light it from above with these glass block skylights and just have this kind of translucent light trickling down onto the gym floor. And his contemporary and also his kind of rival, Del Debbio, was designing a similar building in the Foro Italico, an athletic building in Rome, right at the same time. He had a similar idea. And so what Del Debbio did was he put these right on, he put the glass block skylights right on the main roof level. And so that's a photo of one from the underside. It's just, they're doing everything they can to try to keep these from winking. They're constantly repainting them and dealing with them, and they're kind of covered with mold. And so they're now giving up, and they had covered these with this translucent corrugated fiberglass to try to keep water off them. And what Moretti was smart enough to do is he realized that these were really vulnerable. So instead of putting them right on the roof surface, where it'd have kind of all the flow of the roof just cascading over them and all the sheet flow of water going all the way across that big gym roof, he raised them up on these kind of mushroom-like curbs, and then he also tilted the top of them. So the only water that ever hits them is what hits them directly on the fly. None of the roof washes over them. And then he's tilted them to shed that pretty quickly too. So his are doing well, and Del Debbio is down on the main roof surface or not. So I think great example of just realizing that vulnerability and then making a modification to make yourself less vulnerable to it. And kind of a corollary to that, I think, is to always accept that weathering and general degradation of materials is inevitable, and you just have to account for that. So 2 examples to kind of tie us back, and here in Boston and here in the Back Bay to Italy. So this is an example of Tuscan farmhouse, very vernacular architecture. The large stones here are always chinked or shimmed with smaller stones or little shards of brick. And that's really important. You actually see the same thing. I've worked on a bunch of H.H. Richardson buildings, including Trinity Church right over here in Back Bay. This one's from the Nickerson House in Dedham. But every one of his buildings I've seen the exact same thing. So you see the large stones here, and then these smaller stones, chinking so-called, kind of jammed in between them. And the reason this is really important is mortar is not that durable, particularly in a freeze-thaw environment. So when you have large stones like this, if they left all this space in between here as just mortar, then when that mortar erodes, everything starts to shift around, the stones move around and shift, and walls start to get bulged and displaced and crumble and tumble out. And when this erodes, you've still got all this point-to-point contact to keep everything stable and in place, so it acts more like a dry-laid wall, and that way it becomes just very easily reparable and maintainable and sustainable over time. Easy to keep that going. One example on another Richardson building, this is the Hampden County Courthouse out in Springfield, Mass. Another Richardson building built like almost all his buildings by Norcross Brothers, who I think were just very, very good contractors, and they realized all this. So even though this was ashlar instead of stone masonry, there was basically nothing left of this mortar after 140 years. it was basically just reverted to sand. And they shimmed every stone. In this case, they used slate to kind of fit in there nicely and tighten up the joints and create point-to-point contact between the stones, so that when that mortar just totally deteriorated, they had it was all pinned together with slate. So when we went up here, this is me and one of my colleagues on a 120-foot lift, this was basically a dry laid wall with no mortar 120 feet above the main entrance, and that's what kept that from tumbling down on the main entrance to the courthouse. So we're very thankful they put that slate in 1872 or so. And I think we see a lot of examples of that when you look at traditional arches. This is a building in Boston where those brick in that flat arch actually fell right out of there, and the contractor called and asked me to come out and take a look at it. He said he'd never seen brick fall out of an arch, and the 30 years or so had been doing masonry. And I think what was happening here was they had a very wide mortar joint, and the brick were not cut to wedge shapes. So when you lost the mortar, something like this, that brick was able to drop straight out, and then all of a sudden you had localized instabilities around it, and those brick were able to start dropping out too. And he had kind of shored it with 2-bys by the time I got there before a progressive collapse occurred. And I think it shows the beauty of using a wedge-shaped brick, or in a lot of the Roman construction where they often use a wedge-shaped brick, and where they didn't, what they typically did was the mortar joint goes to basically zero at that inner edge. And I'm kind of diagramming that here with the wedge shape, where you lose this mortar, the wedge shape drops, and it kind of pinches in and locks into a new position of stability, and you don't have a collapse or a loss of stone, and you don't have a progressive collapse. And this is the bridge at the Palazzo Farnese, which is attributed to Michelangelo. And you can see that that's exactly what's occurred here. Rather than one stone, a couple have dropped together, but they've kind of locked in. These have dropped relative to that. They've locked into this new position of stability. Nothing falls, no one gets hurt, and the structure is very reparable. So just shows the beauty of that. And you might say, well, is that really relevant? We don't build too many true load-bearing masonry arches anymore. They're pretty rare these days. But I think that general principle applies to many other things that we do. So this is a diagram of the Miamis River Bridge in Connecticut, I-95, a fatal collapse with 3 fatalities and vehicles dropped into the river off I-95 in 1983. And they just didn't realize that principle. This was a standard Federal Highway Department detail. At that time, it was in the Federal Highway Department handbook. So the right side would be the end of the bridge, cantilever out, similar thing on the other side, and then a pin suspended center. And there are good structural reasons why you would want to do a pin suspended center. A lot of bridges have that, but they had no kind of backup. So you can imagine that these steel pins are very hard to inspect. A person's about this tall trying to look over and see that, and you've got all these road salts and de-icing salts and water washing through here. So it's just a recipe for that to corrode. And when one of the 4, if you imagine in plan, there are 4 of these connections, 2 at each end. When one of the 4 snapped and corroded, then all of a sudden you had all this torque and eccentricity and overload on the other 3 and all the vehicles on them, and those very quickly went too, and the entire section dropped into the river with vehicles on it. And so the modification to this detail was so kind of heartbreakingly simple. What they changed the detail to show in the Federal Highway Manual was a welded plate underneath this on the 4 sides. That's all, simple welded plate. So if this ever corroded, wasn't inspected, something went wrong, this drops onto that little plate that's an inch below, and there's no catastrophic failure. So I think thinking about corrosion, weathering, degradation are inevitable, and you have to build in that plan B. This is a good example of how they did that after the fact, and we wish they had done that before.
Question?
Yes?
Why would they not simply invert the bridge connection and add the span? If it fails, it slips like the stone. Yeah,
we could probably sit here and come up with 12 different ways that they could have very simply done that in a different way that still would have provided the moment-free connection that they were looking for, but had a fail-safe, and they didn't do any of them. It's a great point. So in closing, I'd like to come back again to Vitruvius, and so just some closing thoughts from him. I talked a lot about Book 2, And in book 2, which is all about durability, in my mind, he thought that was really important because book 1 was just what is architecture and what is the role of an architect and defining architecture itself. And then book 2, the very next of the 10 he talks about is durability. So going back to book 1, the very basics, he told us what qualities a building must have to be considered architecture. Not to be considered great architecture, just to be considered architecture. He told us that it must have 3 qualities, and that this applied to all buildings, whether public or private, and whether very grand or simple, modest, residential, utilitarian structures. To be architecture, it must have 3 qualities. And so those 3 are very famously firmitatis, which, I think the kind of the most common translations is the Victorian English Wotton translation of firmness, commodity, delight. But I actually prefer firmitatis as durability, utilitatis is functionality or usefulness, and venustatis, of course, is beauty. So he said it has to have all 3. 2 out of 3 isn't good enough. It has to be right here in the center. And, of course, firmitatis, durability, is the first one he wrote about. And in my mind, that tells me that that's kind of the prerequisite. And it's also the order he listed them in, if you recall, is durability first. So I think he set the bar very high for what architecture needs to be, and I think it's kind of all of our collective goal to try to live up to that bar today. And just kind of in closing, I'd like to say, since this came out of the National Endowment for the Arts grant, and who funded my American Academy Rome Prize, thanking them for all the time there, and all of my Italian colleagues who let me on all their buildings and scaffolds. And here's a pretty apparently long but a very short list of all the people who helped get me onto these buildings. So thanks again to them and for the funding to get me over there, and thank you for coming out this morning and being here early on a Saturday morning.
That was awesome. Mark, if we have a question and answer, should I grab this and hand it to the person so it will get picked up?
Oh, and on your way out, so I do have this little handout, which you're encouraged to take a few of if you have people back in your office. I kind of thought of it as something you could pin up. So it has both the principles summarized, and then also on the back some other suggested reading that you might enjoy if you enjoyed this talk.
Great. Does anybody have any questions?
Could you name 3 institutions here that utilize your firm or imitators of your firm for pre-construction input to avoid the Strata Center type?
Yeah, so institutions that use me or our firm a lot, and you asked about to avoid problems like the Status Center. MIT is one where we do a lot of work. Harvard, I have 4 and just about to start on 5 projects right now. So they definitely use us a lot and value that type of input to avoid problems. And even to go back on these historic buildings, whether traditional or whether more modern, to try to really get to the root of, well, what's been the underlying cause of that problem, and how can we kind of solve that once and for all and not just dress it up.
What happened with MIT and the Strata Center? Did they miss that in their process for the design phase?
Yeah, I don't know exactly. So we weren't involved in the kind of consulting on the original design, and they called us after the fact. I think a lot of times what happens is, a really large commission, they put out for a bunch of proposals. The architects all come in with their team. They have their favorite consultants. And although we're right in the neighborhood and we work a lot for MIT, a lot of times the architect's favorite consultant is in their own neighborhood. So when architects are kind of far-flung, they're often bringing in a team from afar. Sometimes they're reaching out to local people to try to get a local consultant to have boots on the ground, and sometimes not. So sometimes those types of big RFPs result in opportunities to work with someone who we haven't worked with before. I showed the slide of Holyoke Center, now called the Smith Campus Center, and that was put out to a lot of international firms, and Hopkins Architects of London landed that job, and they took as their local architect Brunner Kott, and we work a lot with Brunner Kott, so we've had a chance to work with them on this project and meet someone new, and they're really great, and like working with them. So,
is there a rule of thumb for the cost of your sort of conceptual and design phase input into it?
Yeah, so we often kind of price that up on a case-by-case basis, and I think it can run the gamut from, I think it typically falls into two camps. So there are camps where we're doing kind of more of a peer review and kind of consulting role, so where the architect is the designer of record for the envelope, and they're preparing all the drawings, but when they get a progress set, like a 50 or a 70 or 90%, they send them to us, and we mark up suggestions, and then we'll usually sit down with them and kind of walk them through it and why we're suggesting what we're suggesting and what we think the benefits are. That's kind of one role. And then the other role is sometimes when they have a very large project on their plate, or otherwise they feel it's a little bit out of their wheelhouse of capabilities, where they'll actually peel off and say, you just do all the envelope drawings. So one of my current projects at Harvard is the Lowell House restoration. So that's one of the Neo-Georgian river houses, the largest one, both in terms of square footage, bed size, and it's also got the largest cupola. It's the one with the famous Russian bells in the cupola. And working with Kieran Timberlake on that, who are really great. And in that case, they peeled off the roofing and the walls, and are having us handle that as the designer of record and just do those drawings ourselves. Of course, collaborating with them and making sure everything is going to look the way they want, and it's the slate color that they want and the brick color and everything like that, and that we're matching well. And then actually even on that one, they're doing the window drawings, and we're just doing kind of a consulting role on that. So they're handling any window replacement or restoration.
So each project's determined on its specifics, but there's no rule of thumb like 2% for art.
Yeah, because it varies so widely. I mean, sometimes the red line peer review is, boy, we think we have all this, but we have this one particular question on this thing, or we're a little concerned about this because it's a high humidity building, and we know those can be problematic, so we'd love to get you in for a couple days, a day or two for a working session. And then sometimes it's much more involved, even on the peer review end, and then the design end, I think, is the most involved. So it runs the gamut so much that I don't think there's a typical rule of thumb percentage.
Any other questions?
That was a really fun presentation. Thank you so much. Curious, what is the oldest building? You said Revere's house was the second oldest building in Boston. I was curious what the oldest building is.
Yeah, so I'll repeat just in case the mic didn't pick it up. I mentioned the Paul Revere House is the second oldest building in Boston, 1680 to 83. What's the oldest building? I think Revere House often gets touted as the oldest building, but it is technically the Blake House in Dorchester is a few years older.
And just one other question. In Herculaneum, you mentioned they used that stone, and the mortar was actually more durable than the stone. Why not just use all concrete, why did they use that natural soft stone?
Yeah, the Romans did use a lot of concrete, as you know. I think that's actually kind of another interesting topic. I mean, pretty much everyone knows about the Pantheon, and the Pantheon's often pointed out as a very early example of unreinforced, the only Roman concrete. But pretty much every building that I looked at, any kind of large-scale building in Rome, the markets of Trajan, the Pantheon, like Baths of Caracalla, kind of on, is actually built of concrete. That was really their most common building material. It's not kind of as obviously recognizable as contemporary concrete because they used very large aggregate. And so it's kind of like baseball size, typically, baseball, softball size aggregate. And sometimes they use chunks of stone for that, and sometimes they use chunks of brick for that. And in the case of the Pantheon, there's a whole very, very clever design where the higher they got on the dome, the lighter the aggregate they used to help deal with, just the structural forces on that dome. So they were using things like pumice, which are very light for the aggregate up higher and transitioning. But typically their mortar was very, very hard and was almost analogous to concrete, which is another reason that it's outlasted that stone. The stone's so bad and the mortar's so good. But if you look at broken sections, like if you go to the markets of Trajan, or really any of the baths, it's a good place where you can look at kind of a broken wall section and almost see a section through it. You'll see that there's typically, softball size stone or brick in that stone, and it's just kind of a sea of mortar/concrete. And that's how those walls were typically built. And they almost never exposed it. So, I think another good lesson for durability, that a lot of the brutalist concrete architects could have learned is, concrete's most durable if you don't expose it to the weather. I think they were really being honest about the structure, but the Roman structures, they typically had that sacrificial parge coat of stucco or sometimes brick facing on the structure as the outermost cladding, just because of the greater durability of, say, brick or stone, or the sacrificial nature of the stucco, which would be easy to fix without getting into structural damage to the bearing part of the wall. The Curia Iulia in the Roman Forum, that's one of the earliest buildings in the Forum, is from the 1st century BC. That's Roman concrete faced with brick and then stucco on top of that. And there's actually a tiny bit of stucco that's kind of surviving on the building from the 1st century BC, which is pretty remarkable to see. All the archaeologists swear that's original. So who can guess where would it survive for 2,000 years? Where would you guess? Right underneath the cornice. That's exactly where it is. So kind of our sheltering, overhanging, protecting idea that just basically never gets wet. That's exactly where the 2,000-year-old stucco is.
Isn't one of the reasons that the Roman concrete lasted 2,000 years in the case of the Pantheon is that they used a unique mixture for the soup, including volcanic ash that we don't today. It's actually a better quality concrete than we do today.
Yeah, so they did use volcanic ash, pozzolana, and that's kind of what imparts what we would call the naturally hydraulic quality. So a lot of times when you go back and you look at like a 1600s or 1700s or 1800s building, let's say early 1800s in the U.S., you have a pure lime mortar. And when we talk about lime mortars, they're not very durable at all, and they don't have some of them have a naturally hydraulic property and a lot of them don't. And what that means is, will it set underwater? And how fast will it gain early strength? So the typical lime, if you just bought bagged lime at the local hardware store, that does not have naturally hydraulic properties. And then they talk about naturally hydraulic limes and natural cement, which are basically the same thing, but even more of the natural hydraulic imparting qualities, which are really the pozzolanas. And what those are technically are calcium silicate. So some of the other kind of tradesman rules of thumb of something they can put in, like ground brick dust, is a good pozzolana. Natural pozzolana that you get all around the central Italian peninsula because of all the volcanic activity from Mount Vesuvius, it's essentially a very clayey soil, and then the clay was cooked by the volcanic eruption. So it's very much akin to brick dust in that it's clay that's been vitrified. And you can kind of pick that up all over the ground as you're walking along. If you see, there are kind of two varieties, a very red and a very black, and that's pozzolana. Sometimes you just see like dirt paths or stone paths or gravel paths through the countryside are basically that. So it was all over the place. But that calcium silicate, that kind of fired clay, is the natural ingredient in naturally hydraulic lime and natural cement. And that's also what we put in Portland cement. So it's the same chemical ingredient that gives it that properties. So I guess long story short, both the ancient Roman cement and Roman concrete and our contemporary concrete do have that same ingredient. I think two things they did really well that are why we have 2,000-year-old concrete buildings like the Pantheon, and we're having mid-century 1960s buildings with a lot of concrete deterioration, are they realized, and we realize today, but we have a tough time kind of getting it or enforcing it, is that when you keep the water to cement ratio low, all kinds of good things happen. The concrete's a lot stronger, it's a lot more durable, it's less porous, it's less absorptive. All those things are great for durability. And Of course, contractors often want it soupy because it's more workable. They can, they can make sure they get it to flow around all the bars easily. They can pour it easily. They can pump it. If they're pumping concrete in this particular place, they can get it up there. If it's too thick, they can't pump it up high on a building. So engineers are always stressing the maximum water-cement ratio, and contractors always want more, and we're always fighting about that. So the Romans got that, and so their concrete, instead of being like a sour cream consistency, it was much more like peanut butter. It was really stiff, really low, and they really packed it. So it was stiff enough that they were kind of packing it in with trowels and kind of battering it. And Vitruvius talks about this. And there's a mural from Pompeii that's now in the Archaeological Museum in Naples that shows them building a wall, and they're kind of slamming it in. And so density, keeping the water-cement ratio low, they got that. They were really good at that. And the other key thing is, usually the Achilles heel in our modern concrete is what? What causes it to deteriorate? When you usually see a big pop or spall in concrete, what's always under it? Steel, rusted steel, right? They didn't reinforce it. So they essentially have eliminated the Achilles heel right there. Eliminating the steel meant that they had to design compressive structures like domes and arches. They weren't designing flat slabs. But they were good at designing vaults and arches and domes, and so they built with it almost like it was just natural cut stone. So they didn't need the reinforcing, and that was a huge benefit for durability.
One more question?
I already asked one. From a builder's perspective, my speculation, part of the exterior spalling concrete and that is architects allowing builders to talk about pouring concrete rather than placing. I grew up with a traditionalist builder who said you do not pour. That's what house builders do. They water down the concrete just to get it done as quickly. They pour it. You place concrete because the mix should be a much lower ratio of water to cement.
Right.
And all the porosity that occurs.
And it's almost counterintuitive because a lot of builders might think that, boy, if I pour it, it's really fluid. There aren't going to be any voids in there, right? It's like soup, and how can you have a void? And when it's kind of dry and stiff, you might think there are little places in there. But when you think about it, when it's cured, all the water's gone, right? So the more water you put into the original mix, that's more material that's disappearing as it's kind of shrinking and consolidating and all that. So there's kind of the logic of it.
Therefore, eradicate the use of pour and make it.
Yeah, one thing that's helping today, one way that technology is helping today are admixtures like superplasticizers. So you've got a very small quantity of a chemical that, essentially is like a lubricant, right? So it makes the concrete flow a lot better and pour a lot better and move around congested rebar and stuff and fill in the voids, but it doesn't add much water. So it takes a small amount of superplasticizer, takes the place of a lot of water. So that's often where we kind of wind up as a compromise, as we say we want 0.40 water cement content max, and they're like, that's not workable. And then we've got 0.40 but a superplasticizer to make us both happy.
On that note, one more.